Here we go. Good morning, everyone. Such a pleasure being here again. Super excited to be physically in a conference with people, with eyes, not in a screen. It's pretty exciting. Today, I'm super excited to talk to you about some new concurrency features that came to Swift recently. And I'm just going to go straight into it because we have a lot of content to talk about today. So first of all, quickly introduce myself. My name is Shai. I'm a tech lead in a company called Money.com. I'm doing a lot of open source work, most notably Arc, Swift, and Combine related open source projects. And I love speaking in conferences, exactly like this one. Also writing and editing for RayWonderlic.com, which some of you might know, content producer for iOS, Android, and Flutter. These are some of the books I had the pleasure of working on. So let's get right to it. Let's talk a bit about concurrency. So first of all, what is concurrency? Concurrency is just the ability to execute more than one program or a piece of work simultaneously together with other pieces of work. So let's make a pizza to demonstrate that. I have to say from the get-go, I know I'm in Italy. This isn't an actual pizza recipe. Don't grab me later and say, Shai, that was not cool of you. So just enjoy the example. So let's talk about the difference between serial and concurrent execution. So maybe in serial execution, I might make my dough and rise it. Then I will wait, and then I would heat the oven. Finally, I would make and add some sauce, add some mushrooms, add some olives, and finally, I would bake my pizza, and I would have a prepared pizza. And this will take, again, not actual pizza recipe, very important. This would take like an hour, 47 minutes in this very rough calculation. With concurrent execution, maybe we can make this a bit more efficient. Maybe while I'm making and rising the dough, I can actually make the sauce while I'm waiting for the dough to rise. Maybe I can even preheat the oven while I'm waiting. Then I can just add the sauce I pre-made. Maybe I can add all of the toppings together instead of having to do them one after the other. And finally, I can bake the pizza. And I get the same result, and it takes me like substantially less time. But we can kind of go on the macro level here. So for example, if I have a single pizza shop, maybe I can make 3 pizzas in about 4 hours or so. But if I have 3 separate pizza shops, I can actually make 3 pizzas in the time it takes to make a single one. So this is another form of concurrency or parallelism. Let's talk a bit about what we have before the new Async 08 features, what we worked with until today. So the things you're kind of most familiar with are going to be Grand Central Dispatch, things like dispatch queues. We have completion handlers to notify us when long-running asynchronous work is running. And we also have Combine, which is kind of the new kid on the block, 2 years old or so. So let's talk about like a very common task of fetching a single resource asynchronously. So today, if I want to run some code synchronously, I might run this load image and block. Oop. Yeah. So I might write in this load image and just block the current thread. This is synchronous, so it's pretty easy to read, but it's not very efficient because it's going to block the current thread. On the other hand, we might have this closure-based version that would work asynchronously. I pass a closure to it, and then I update the avatar when I get the result later on. What happens when I want to update multiple pieces of data? So for example, here on the left, I have this same synchronous variation. The remote isn't working very well. Here we go. So I might do a load image, then load invites count, load friends, but each of this is going to block the thread and wait for the previous piece of work to finish while blocking and not allowing any other piece of work to run on the current thread. On the other side, we have asynchronous work. We can just kind of make this pyramid of doom-like thing and nest all our pieces of work to get the data. And then inside the most inner closure, we will get all of the data and work with it together. But what if you want to actually run a lot of work in parallel? For example, we want to load the image, load the invites, load the friends, do all of that together without waiting for each other, and only at the end work with all the piece of data. So today, the main option we have is dispatch groups, which is very verbose, as you can see. It's a lot of code to work with. We kind of have to enter and leave every group as we run our code, and eventually we have to do this notify thing. So it's a lot of work and very easy to get wrong. We have some other options like using semaphores and dispatch work items, and of course combined publishers, but they are a bit more involved. So my point is really that concurrency is just hard. When I started iOS in 2010, there wasn't so much concurrency. We had basically single CPU devices. We ran a lot of stuff on the main thread. So even for me, when I just started, trying to figure out what it is and how to run stuff off the main thread was very, very challenging. And actually a bit of a fan moment here myself. The person that first explained it to me was Matt Thompson, who made Alamo Fire and AF networking. So for me, it's been also hard, like a lot of other developers coming into Swift and iOS development. So our code got much more modern. We got stuff like Swift, and we got stuff like SwiftUI, but concurrency and concurrency-related code really didn't get any easier. We are working with the same tools that we have for almost a decade now. But we have some good stuff on both sides. So for example, synchronous code is very easy to read and very easy to follow, and it's very predictable because we can just write it serially in a line. And it does very simple error handling because we can just try, throw, and catch. On the other side, for asynchronous code, we can get concurrent execution. We are not blocking the main thread. We can use multiple threads, which leads to optimum resource optimization. And if we look at the bad sides, we actually get the exact flip side of that. So for synchronous code, it is serial, it's blocking. We can only work on a single thread, and we have very poor resource utilization. And for asynchronous code, it's very difficult to follow because we have all of this nesting and all of these nested closures. It's sometimes unpredictable, especially when it gets a lot of different asynchronous work, a piece of work together. And handling works, different errors thrown around is much more involved and error-prone in itself. So many others in the Swift community thought that the situation of that is not optimal, to say the least. Most notably, this one very smart person called Chris Latner. If you don't know him, he invented Swift. Basically, he made the main offer for Swift, LLVM and Clang. And he wrote this document called the Swift Concurrency Manifesto. And if you look at the date, this is back in 2017. So this has been for a long time in the work. And as part of the proposition and everything, they realized that async await might be a great solution for this moving forward. But what is this async await that I keep throwing around and people kind of talk about around us? So basically, it's async and await. No, I'm kidding, obviously. Very poor joke. But no, async await is actually a new syntax, and it's part of a new set of features in Swift called Swift Concurrency. We know these keywords from other programming languages, so it's kind of a mature way to reason about and talk about asynchronous work and how to run it, handle it, and manage it. It's implemented a bit differently in every language, but still it's nice having a common way to talk about this stuff across languages. So when you use the word async, it lets you define an asynchronous function. So for example, here I have this load image that gets a completion handler. I can just turn this into an async throws function. I will take the result type and just put the return type in the return just like a regular synchronous function. And since I can get an error, I will just make it a throwing function. So this is much simpler. It's much simpler to read, and I know exactly that it will be a long-running task that works asynchronously. It might throw an error, and I don't have to guess what will happen inside this completion handler, for example. Await on the other side lets you wait on these asynchronous functions. So instead of having to call a load image like this, and then pass a closure, and then wait for success or failure, I can simply do try await on this load image asynchronous function and wrap it in the do catch, just like synchronous code. So it makes the code very, very simple and very, very succinct. You might ask yourself, can I just run this asynchronous code and await everywhere in my app? The answer is no, the compiler will not let you. You have to be in a very specific context to run asynchronous functions. More specifically, you have to be in an asynchronous context. So that means mainly two things. You either have to be in a different async function, and then you can await from it with no problem. And the second option is creating a task. A task is a new asynchronous context where you can run these pieces of work. So here, I'm initializing a task, and then I can just await inside of it, and that way the compiler is happy. So this might be a bit confusing to kind of fathom to begin with, but these two pieces of code are inherently similar. On the left side, we have the nested closure based, and on the right side, we have the await-based pieces of code, but they're both always waiting for the result of the previous piece of work and moving forward when that was done. So again, this reads synchronous, which is a huge benefit, but it runs synchronous, it doesn't block the thread, it just suspends. We're going to talk a bit more about the mechanism of how this stuff works in a bit, but it just suspends each function and waits for the result before moving to the next piece of work that's available for it. And it's pretty amazing. You'll see a bit more about that. So if we take all the good of synchronous and asynchronous, really we are getting async await, because we get all the good side of writing very succinct and simple code, but we get all the benefits of CPU utilization, parallelization, all that stuff. So now a bit about how does it work under the hood. So we talked a bit about task. Task is really the main unit of asynchronous work in Swift. It could have relations between tasks. You could have a parent task with child tasks and stuff like that. Basically, we get initializers that let us create these new asynchronous contexts. We saw one of these earlier. For example, this task initializer. When you use this, it's going to inherit the current context and stuff like task values, etc. So here, for example, I'm on a view controller. And the view controller is tied to something called the main actor. We'll talk about that a bit later. But it means that inside this task, I'm actually on the main thread because I'm inheriting the context of the view controller. I can also use task.detached, which will remove that. It basically detaches the task from the current context, and it doesn't inherit all of these things, and then you just are running on some thread. And while task just looks like a simple initializer, it's actually a type, and it's generic over this success and failure type. So standardly, there are just void and never, but we can put anything we want in there, and we can even just do a wait task value to wait value of that specific task. It's not very common to do this, but it is how it works under the hood. Also, Swift Concurrency, I think that's one of the most interesting things about how it works is that it completely changed the concurrency model. It's not just like nice syntax around dispatch queues. It just works completely differently. It uses this concept called a cooperative thread pool. Here's a pool of threads. Anyways, so the way it works is that we have a pool of threads that are available to run our different pieces of asynchronous code. And there is one rule for tasks that they always have to make some forward progress or suspend. So you can't just block the thread or add a lock that and never unlock it and stuff like that, because that's breaking the contract of Swift Concurrency. You only get one thread per CPU core. If you've been working with dispatch queues, for example, there is a common thing called thread explosion, that if you have a queue and you block it for some reason, you might keep spawning endless amount of threads, far more than you have CPU cores. And that can create a lot of performance penalties and a lot of issues in your app. So this kind of avoids this situation and all the overhead of thread explosion and thread switching and all that stuff. And it does this by, instead of switching threads completely, it uses this kind of lightweight abstraction called a continuation. And I will show you in a minute how it does this without switching threads, basically. So when we mark functions async, like I showed you earlier, it tells Swift, okay, you can give up the thread, you can suspend yourself. What does that mean? Here, for example, I have this getFoo function, and internally it's awaiting this getAmazingItem. When it sees this await, getFoo says, okay, I'm suspending now. I'm waiting for this getAmazingItem to finish, and whatever thread I'm running on, I'm giving it up. Someone else can now utilize this resource instead of me. And then when we want to execute getAmazingItem, it might run immediately, or it might also suspend itself, depending on if there is higher priority pieces of work or something more important that needs to run before. And this is all managed for you automatically. But the point is that getFoo suspend and just waits, and then when we get the data back from getAmazingItem, only then do something will be executed with that piece of data. So again, it's just like this very fancy mechanism, but when you look at the code, it's very, very simple, and you don't really have to think about it too much. It has very good CPU utilization, because it kind of just always makes sure that all of your threads are busy and all the high priority work automatically gets the execution rights. I want to show you a few more really cool things you can do with async await in your code base. So we talked a bit about error handling. As you know, if you've been working with Swift or Objective-C, error handling up until now was quite rough. So we have this nested pyramid of doom here. And internally, like, how do we deal with all of these three errors? How do we deal with cancellation? What happens if I don't want to run load friends? I actually want to stop after load image because something happened. Maybe I got an error. So it makes everything quite hard to short circuit and stop execution. If we look on the async await variant of this, so aside for looking much, much simpler to read, again, synchronously read but asynchronously executed, if any of the tasks are failing, it is not going to move on to the next one. So if load image throws, it would just stop execution, go to the catch block exactly like you expect, and would cancel the other pending tasks. Also, it kind of gives the compiler some ability to watch over you and prevent you from making stupid mistakes. For example, this is a very common piece of code. We have this function that gets a completion handler, and it just fetches the resource and then completes with the success of that resource. But the keen eye of you might have noticed that I just put an else return here instinctively, and I didn't handle the error case here. So I didn't do a completion with failure in this case, and if something went wrong, no one is going to know about it. If I switch this function to an async function, this is impossible to do. The compiler won't let me do this. It's going to tell me that it is a non-void function. You have to return something from it or handle it somehow. And then it forces you to think about the problem and fix it. In my case, I can just throw an error because it's a regular async function. I don't have to do anything fancy to solve it. Async isn't limited to just functions. We can actually also make getters asynchronous, which is a new, very useful addition. For example, I can take a person and add this var avatar. Notice that it has an explicit getter that is get, async, and throws, like a function. And that means that when you are going to access Shai.avatar, for example, you will have to await that getter, like you await a function. But sometimes a property makes more sense contextually, and you can do both depending on what fits your scenario. Another thing I really like to talk about is like how we can solve very convoluted flows that are very hard to get right with closures with async await. This is a very common flow that we actually have in one of our apps of JWT token refresher, which is kind of a known tricky thing to get right. So if we have a refresh token that's about to expire, we might want to renew the lease on that refresh token, and then we would use the valid refresh token we have to refresh the access token. Then we can get some resource like a user and return that back. And of course, we have to deal with all of the errors that result from each of these steps. So if we use closures, then we have to do something like this. Basically, once we renew the token, we actually have to recurse back into the function with the same completion handler because we don't have a way to say, okay, go renew the topic and when you renew the token, sorry, and when you're done, just continue going downwards in the control flow. We don't have a way to do that with asynchronous logic because of this closure-based ad hoc logic. But if we switch to async await, not only it becomes much shorter and easier to understand, we don't have to recurse back into the function. We just renew whenever it suspends the refresh token if needed function, and when the renewal is done, it's just going to proceed downwards like a regular synchronous function without having to mess around and fiddle with all sorts of completion handlers, which is very, very nice and very useful. And as you can see, it's very easy to reason about this code. You could probably understand how it works without me explaining it. So back to our person info example from before. We talked about asynchronous execution that is kind of straight line, which is really nice. But here we are still awaiting for each resource separately. What if we want to parallelize? We want to run all of them together and wait for their accumulative result. So we saw this piece of code with a dispatch group earlier. And the way you solve this in async await is something called an async let binding. So when you use async let, you tell the runtime, okay, I'm going to have a few different pieces of data, and I'm going to await all of them together at some point. So here, I just await handle info with my 3 asynchronous pieces of content, and only then it's going to run all of them, but it won't wait serially. It will run all of them together, and when the piece of work is done, only then it's going to hand it off to handle info to do its work. So this is a very nice syntax, and also if again, like look at the size of code that we are reducing here, but also the readability and understandability of it. What about cancellation? We talked about task cancellation and how that can get quite tricky with closures. So for example, this is a good example. I have this getter of avatar, and I'm getting the user data, and then I will use the data to construct a UI image. But actually, maybe the task was canceled right after I got the data, and maybe I don't want to create an image from it, but I want to stop or want to do something else. So the first thing I can do is use this thing called task.check cancellation. And what it does, it check, was I canceled? If you were canceled, it will just stop the execution by throwing a special error called a cancellation error, and that's going to tell all the tasks above it, hey, I was canceled, just FYI. You might actually want to do something different, like controlling the control flow instead of entirely terminating the task. And you can do that by just checking the global if task is canceled, and it would again just check if the current task is canceled, and you can have entirely different logic in that case. Here I am just returning that that placeholder instead of actually returning the image data. Lastly, we can use this thing called a with task cancellation error. We wrap our operation, which is our asynchronous work, and we add this onCancel closure, and then this onCancel is just it's immediately executed when the task is canceled. This is really good for cleanup or like other side effective things like clearing a cache and stuff like that. Let's quickly switch to task groups, which are one of the best features and most useful features of async await, in my opinion. So let's talk about a scenario where we want to run a lot of pieces of work together. And I'm not talking 2 or 3 pieces, I mean in like hundreds, for example. So we have a list of people, and you want to fetch all of their images, all of their avatars, and gather them into this array of assets. So you might be tempted to just iterate over them in a for loop and then await each of the results. And this will work, but it's very not performant just because it's serial. So this await is going to wait for each avatar in line. If you have a list of 100 people, it will wait 100 times for all these avatars to complete instead of running, I know, 100 requests together and waiting for the images to come back. You might say, okay, Shai, just a second ago you talked about async-let bindings, running stuff in parallel. Maybe we can use that. Not really, because async-let works when you know exactly how many pieces of work you're going to execute. In our previous example, we knew we have 3 different items. We are waiting on all of them, and we will mark them as async-let and then await them together. But here, what am I going to write after this async-let? I can't just add it to an array because the compiler is going to complain. So this is a bit of a problem. So luckily, the good folks at Swift invented this awesome thing called a task group. And the way it works, as you can imagine from the name, it groups other tasks in a single, bigger parent task in a very hierarchical way. And you can use either with task group or throwing task group, depends on if your internal piece of work might throw an error. And inside here, you will fill up the type of resource you want to fetch. So for example, in my case, I want to fetch user images, so I will put UI image here. And then inside of the closure, I can just add as many tasks as I want. So here I'm iterating over my people list, but I'm adding a task to the group and awaiting every time internally. And then I can simply await image in group. I can just iterate over the group's result asynchronously, and I'm going to get the results as they come in, and all of the load images are going to run together with each other. And I'm only going to get to this return result. I'm only going to get to the return result when all of the different pieces of asynchronous work are complete. And it's also pretty nice because if one of the tasks fail, you can expect the entire task to fail unless you handle it differently. You can also add priorities to tasks. For example, here I might have a person that is very important and I want to load their image first. So I can just mark the priority of the task as high versus nil, which is the default priority for tasks. One important thing to understand about task groups is there is no guarantee of the execution order. So if you're on 100 tasks, there is no guarantee that you are going to get them back in the order you executed them. So it's important to have some mechanism to associate the image with the user, for example. So here, instead of a task group of image, I'm making a task group of a tuple of a UUID and a UI image, and then I just associate the avatar with the user ID. And notice that I'm awaiting this entire expression, even though person ID is synchronous. This is exactly like a try statement. You can try an entire statement, even if just a portion of it is throwing. So here you can await an entire statement, even if just a portion of it is asynchronous. And then I can just iterate over the group resort, and I can even use stuff like reduce that are reserved to Swift sequences. And we get all these overloads to just put all of the images in a dictionary that associates each ID to the fetched image. A quick word on structured and unstructured concurrency. This is a very deep topic. I'm not going to like really go deep into it, but just so you understand, when we talk about structured concurrency, we are talking about hierarchy between tasks. For example, task groups are like a very good example of this. We have a group, and there is a hierarchy between that group and all these child tasks. And it lets Swift do nice things, like if the task group is canceled, it automatically kind of funnels that cancellation downwards toward the child tasks. If we're talking about unstructured concurrency, we're talking about the other way around. We have tasks that are independent and they are not tied to any other pieces of work. And we can already see the two examples we mentioned earlier, like task and task detached, that are not tied to any other specific parent task. So a bit about async sequence. So you don't know this, but I'm pretty excited about it because you already know this. Like I just showed you an example of how this works. But the way it works is that today, we talked about mainly how to fetch a single piece of data. We had a load image or a load avatar or whatever, but often you will have methods or pieces of work that will return more than a single value. And combined publishers are a very good example of that. You can have things like sockets or publishers or file handles, or even a URL request might return a lot of data and not just a single result. And that's a prime use case for async sequences. And the way they work is that they are just the same in a sense, like a regular Swift sequence, which is like an array or a dictionary, just that every value is awaited asynchronously instead of just being available as you wait for it. You've already seen this with task groups, which is why I'm saying that you already know this. But here, this area where we are awaiting every image in the group is actually an async sequence. And when we do for await image in group, we are awaiting every element in this large, potentially endless asynchronous sequence, and we'll only get to this return result when the entire collection of work is done, basically. There are a few built-in ways that Swift already uses async sequences, and I just want to show you two very quick examples so you know what are the possible use cases for it. So the first one is URL request, which is the most common. So let's say you have a very huge CSV file with a list of people and their IDs. Let's say it has like 500,000 lines, very, very big file. So you might be tempted to just fetch the data for that file, get all the people, you get the data and turn it into a string, split the string into new lines, and then iterate over all of the lines and make a bunch of people from that list. This will work, but it's not very performant because we are fetching the entire file, we are parsing the entire file, and we also have to work with a very, very large piece of data in string. What we can do with async sequences is use this new bytes API. So here, we are actually using this bytes API that provides bytes.lines, and we can await each line in the request lazily. So while the data is being pushed towards you, you're getting them line by line or in chunks, but you don't have to take in the entire file into memory. You get the data as it kind of comes from the server. You can do the same with files, actually. So instead of having to load the entire contents of the file, you can use this new API of file handle that gives you handle bytes lines. So you can iterate over the lines in a file locally to your system without having to put the entire file into memory and process the entire chunk of data together. So again, very, very useful and very efficient for processing a lot of data. Async sequence is simply a protocol. You can easily conform to it and make your own async sequences, but actually you don't really need to, and we'll get to why in a moment. Let's do a quick detour to actors. So actors is like a super, super broad topic. I'm only going to focus on the things that are like must know. And there is a really good WWDC session called Protect Mutable State with Swift Actors that you should really check out. So we'll go into the basics of this today, though. So if you have worked with any form of asynchronous work, you know that one of the trickiest things to get right is data races, which means an unexpected change to your state. For example, if I have two separate threads running some work, and they are both accessing some shared mutable state, that's always the keyword. It has to be some shared state with multiple accesses, and one of those accesses has to be a mutation, a write. So it might be quite common that one of these threads will either get the wrong result back, or you will just outright crash because there was some inconsistency or race in your access to the data. To Today, the tools we have to solve these are things like manually locking the thread using like an NS lock or a recursive lock, or we can even use stuff like serial dispatch queues. And these things work well, but they are very, very hard to get right. You might write code that looks like it is working, but in reality, in production, it might not behave because you misused the API. So actors are a really cool solution to this problem that was brought in with the entire suite of new concurrency features. And it is a class-like object, meaning it's a reference type. And it provides automatic synchronization and isolation for the state. So it automatically does this entire locking and unlocking for you to protect its own state from getting into these thread racing conditions. It's coming from other languages like Akka and Erlang that kind of started this thing, and Swift kind of made its own take on it. So an actor can read and write its own state and data synchronously, no problem. But if we have a different actor, and it's trying to change something in this other actor, it has to do so asynchronously by awaiting that change. And this is the way it works. I'll show you, for example, this is a very common example that you will see in some code bases, maybe with more complex data, but still. We have a list of items here, and we have an index. And the index says which person I'm on right now, and I have a next method. And the next method just increments the index and prints out the next person in line. If I would try to kind of concurrently run this 3 times on 3 different queues, what do you think will be the result here? Show of hand or throw out? Well, I think that you might not be surprised to know that it would just print my name 3 times. And this just happens to be the case on my computer. It might be different on different computers. The reason is that index is mutated, trying to be mutated from 3 different queues, and there is no way to make sure that the increment finished before we are printing the data. So the index is stuck on 0 when we attempt to print it in this next method. But if we just swap out class for actor, first of all, I can't do this anymore. The compiler won't let me. It says that next cannot be referenced from the main actor. What we can do instead is use a task and await each of these next methods. And notice I didn't have to put an async on this next function. It automatically becomes awaitable. And when you do this, you're going to get exactly the result that you expect, because the actor automatically protects you and protects the state internally. So you don't have to mess with locks and all of this stuff by hand. There's another special, very useful and common kind of actor called the main actor. And it's special because it represents directly the main thread. So if we run stuff on the main actor, it is parallel to just doing dispatch queue.main.async. You can annotate an entire class type or even a specific function with @main_actor. It's very common for stuff like a view model or view controller, stuff like that. You can say all of these functions and all of the content of this class are isolated to the main actor or the main thread. And you can also opt out of this for specific pieces of work, like this does non-UI thing uses non-isolated, which means it is not isolated to the main actor. It can run on any actor, while the other things in the class are still going to be constrained to the main thread. There's a bunch more content here on actors. I'm not going to touch on that today, but I kind of implore you to check it out and learn about it, because it's very, very interesting things if you're going to use actors to protect your data. Finally, my favorite section is how can you take all of these features that I showed you today and kind of use them in your own code base starting today. So first thing about deployment target, very important. And the nice thing is that it's all available for all of us from iOS 13 and up. And that wasn't always the case. For a moment now, some of us were sure we're going to have to upgrade to iOS 15 just to use these features. But with the great work of the Swift team and Doug Greger specifically, we got this concurrency compatibility library that automatically lets us backport all the way back to iOS 13. So you can use async await in most modern-ish code bases. You can also create your own continuations. We talked about continuations very briefly earlier, but what it means really is that up until now, we just work with async functions that just call out to different pieces of work. But you might have a lot of existing code that already uses closures or uses publishers or using some other form of work, and you want to wrap them inside this async await context. And the way to do this is with either of these 4 functions. for example, with checked continuation or throw-in continuation will let you either throw or not throw within the task. And the way it works is if I have this closure-based function, like load image, it gets a completion handler. I can wrap it using with checked throw-in continuation. I get back a continuation as an argument here. And then on the success or failure, I can either resume returning a result or resume by throwing an error. I can even shorten this further because continuation supports just passing a result type into it. So you can just do continuation resume with a result, and then you're just calling your closure-based load image internally, but you're also exposing an async load image. So you have the best of both worlds. You can also backward support this way. Oh, a very important note here is that you mustn't resume the continuation more than once. So you can either resume with a result or resume with an error. But if you do it more than once, then the Swift runtime is just going to throw a bunch of errors at you and will act a bit unpredictably. And what about async sequences? We talked about how to use them, but not really about how to create them yourself. So we said it's a protocol and that you don't actually have to conform to it because there is already a type that does this. It's called async stream. It already conforms to this protocol for you. And what you can do, for example, this is a piece of work called monitor stocks. It just gets a closure and it sort of emits stock changes. It might emit that a stock change to a certain value, and when there are no more values, it will just emit this finished case in the enum instead. So I can just wrap it in this async stream. I get again a continuation, but this continuation is different because it can accept multiple values. So I just call my closure-based monitor stocks, and whenever there's a change, I yield that change to the continuation, and whenever I'm done, I just do continuation finished. And then on the right side, you can see that I can just do for await stock in monitor stocks. And this is, again, this is my async-based function. And I'm using this internally, the old code I have, but I'm working with all the new tooling that are available for async await. So this might seem like a strange topic to talk about, a bit dinosaur-like about Objective-C interop, but there's a good reason for this. So for Objective-C code, the Swift compiler automatically synthesizes async versions of block-based methods. For example, this is a fetch numbers method in Objective-C. It gets a closure that passes an array, and you will see that you automatically get a fetch numbers function that is async without doing anything. The runtime just does this for you. You can even further enhance these methods by providing your own name or your own refinements to these functions. For example, here I thought that just calling it numbers makes more sense for Swift async functions, so I just use ns Swift async name to do that. The reason this is so important is that most of the code that we work on the day-to-day, like UIKit and stuff, still uses Objective-C. So we get all this bridging for free. And all of these existing stuff like HealthKit is a good example of that uses a lot of Objective-C based blocks. You get async variants for free without doing any work. The two last topics for today are a bit about SwiftUI and Combine. So you might ask yourself, how do I use this stuff with SwiftUI? So if you're using iOS 15 and up, there is this nice modifier called task. You just attach it to your view, and you get an asynchronous context to run your work in. If you're only supporting iOS 13 and up, you can kind of simulate this by just creating a new task on the onAppear of your view and then doing your work here. This is a bit different because the task modifier actually takes care of things like canceling your work when you exit the view and stuff like that, but it's still possible to achieve a pretty similar effect in iOS 13 and up. You might ask yourself also, what about Combine? Because we did talk about async sequence, and if you work with Combine or RX, you probably see the similarity. We have this stream of endless values that might finish at some point. So you're absolutely right. They are actually quite parallel. You can even kind of bridge between them. Here I have this Combine code that just gets a publisher of numbers, maps over it, gets only the first three items and drops the first. And then I just used sync to print the values. But what I can do instead in async await is use this new .values property on publishers. And this just turned the publisher into an async sequence. And then instead of doing .sync, I can just do for await value in publisher values, and I get the exact same effect, but with much simpler code and very similar to, again, synchronous code. And I can use kind of bridge combine back and forth this way into async await. But you also might ask yourself, what about all the awesome operators? Like we saw stuff like map and filter and reduce and stuff like that. And we don't really have them in async await. But actually, as of last week, we kind of do, because Apple are very strongly pushing us towards using async await over combine, it seems. They just released this new library called Swift Async Algorithms, which has a bunch of very useful operators, operator-like things for async operations, for async sequences. So here we have combine latest and merge, things that kind of come from Rx and combine if you've ever worked with them. And you can use these same constructs inside async sequences. So if you want to learn more or a bit deeper into some of these topics, I suggest picking up our new book that Marin Todorov wrote and I edited. You can grab it at swiftasync08.com if you want to support our work. And finally, free book time. I love to do this every time. Take out your phone or write the link. I can also send it a bit later. Just sign up on this form. And when we're done today, I will send you some 5 or 6 free books to the registrants. And that's it. I'm done. Thank you so much for your time and enjoy the rest of the conference.